welcome to this explainer. Okay, today we are decoding the molecular language of carbon. If you've ever stared at a massive chemical name or one of those chaotic zigzag diagrams and just felt your eyes completely glaze over, yeah, don't worry. We're going to translate all of that into a really sleek logical code.
So, let's dive right in with a massive question. How on earth do scientists organize the absolute chaos of millions of different molecular structures that make up our physical world? I mean, from the food we eat to the fuels we burn, literally down to the DNA inside our cells, how do we actually keep track of it all without losing our minds?
Well, it all starts with organic chemistry, and that is essentially just the study of carbon-containing compounds. Now, there are a few inorganic exceptions, things like carbon monoxide, carbon dioxide, and carbonates, but other than those, this is the framework for the vast majority of carbon molecules in our entire universe. Here is our roadmap for today as molecular translators: carbon's unique combination power, visualizing organic molecules, families of carbon compounds, the IUPAC naming system, and finally, cracking branched carbon chains. Let's get to it. Section 1. Carbon's unique combination power, the ultimate building block. Okay, so carbon acts like the absolute ultimate connective Lego brick of the universe. And what makes it so incredibly versatile is that each atom can form 4 separate bonds, right? Because it has these 4 connection points, it can easily join up with other carbon atoms to form endless chains and rings. It can even form double or triple bonds with itself. And honestly, it doesn't stop there. It combines so easily with a whole host of other elements: hydrogen, oxygen, chlorine, nitrogen, sulfur. It's a real game changer. And you can see that versatility perfectly right here. Carbon atoms can physically connect to form these long, straight, continuous chains, or they can form complex side chains branching off the main line, or they can even loop all the way back around onto themselves to form continuous ring shapes. It's absolutely amazing. Section 2. Visualizing organic molecules, from 2D drawings to 3D reality. The contrast we're looking at here is pretty striking. On the left, you've got standard 2D structural formulas, like butane and 2-methylpropane. Those are perfect for showing exactly which atoms hook up to which. But check out the ball and stick and space-filling models on the right. That reveals their true 3D tetrahedral reality. They aren't just flat little grids on a page. They are complex, 3-dimensional shapes. Now, drawing out every single bond in 2D takes a lot of time. So chemists use condensed structural formulas. They basically just skip drawing the structural lines for the single bonds that join hydrogen atoms to the main carbon chain. They just write CH3 or CH2 instead. It makes the whole structure way faster to write down and a lot easier to read at a glance, while still giving you the exact same structural info. One quick note though, carbon-carbon double or triple bonds, yeah, you still have to draw those out. Section 3. Families of carbon compounds, the power of functional groups. Let's compare 2 really closely related molecules, ethane and ethanol. The difference between them is wild. Ethane is a gas at room temperature, and it has absolutely zero reaction to sodium. Ethanol, on the other hand, it's a liquid at room temperature that reacts vigorously with sodium to release hydrogen gas. So the crucial takeaway here is that this massive shift in physical properties is caused by just one tiny alteration. Ethanol is basically just ethane, but one single hydrogen atom has been swapped out for an oxygen-hydrogen pairing. That's a hydroxyl functional group, which you can see circled in green. A functional group is just an atom or a group of atoms that completely determines most of the properties of an organic compound. It literally modifies how the whole carbon skeleton behaves. Section 4. The IUPAC naming system. Translating the code. Okay, consider this your ultimate cheat sheet. In the IUPAC system, the prefix tells you exactly how many carbon atoms are in the longest chain. 1 is meth, 2 is F, 3 is prop, all the way up to hex for 6. If you memorize these, you can instantly know the fundamental size of any carbon chain just by reading the very first part of its name. Now, while the prefix tells us the chain length, the suffix acts like the grammar. It tells us about the bonds and the overall structure. So if a name ends in ane, like in alkanes, it means the carbon atoms are connected strictly by single bonds. If it ends in ene, like an alkene, boom, it contains at least one double bond. And if a piece of a molecule ends in -yle, that means it's an alkyl group. That's basically just a branch sticking off the side of your main carbon chain. Section 5. Cracking branched carbon chains, putting the rules together. Please do not let massive hyphenated chemical names freak you out. Seriously, they are just a set of instructions. Just follow these 4 systematic steps to decode exactly how a molecule is built. First, find the longest continuous carbon chain. That's your root name. Second, number the carbons in that chain so that any attached branches sit on the lowest possible numbers. Third, name those branches or substituents and tag them with their number. And finally, step 4, if you have different types of branches, just arrange their names alphabetically. Easy. Watching this play out in action makes it so much clearer. Let's actually trace this structure. First, we find the longest continuous chain, which has 6 carbons. So our root word is hexane. Next, we need to number that chain. If we go left to right, our branches land on carbons 3, 4, 5, and 5. But if we number from right to left, they land on 2, 2, 3, and 4. The rule is to give branches the smallest values possible, so we definitely go right to left. Now let's look at the branches themselves. We've got 3 identical 1-carbon branches. Those are methyl groups. Because there are 3 of them, we group them together with the prefix tri, making it trimethyl located at carbons 2, 2, and 4. We also have a 2-carbon branch, an ethyl group, sitting at carbon 3. Notice how we arrange the final name here. We put ethyl before methyl because we always alphabetize the root words. The tri-multiplier doesn't count for alphabetical order, so putting it all together, it becomes 3-ethyl-2,2,4-trimethylhexane. And you know what? These systematic rules apply everywhere, even when functional groups change. Take a look at this alkene molecule. The rule here is that the carbon-carbon double bond gets priority. So we number the 6-carbon chain from left to right to make sure the double bond gets the smaller number, 2, instead of numbering right to left, which would slap it with a 4. We also have a methyl branch sitting at position 4. So perfectly translating this visual structure gives us the name 4-methyl-hex-2-ene. It really is like learning to read an entirely new language. Once you understand the basic rules of this molecular grammar, the prefixes, the suffixes, and the numbering system, an entire invisible world of organic chemistry suddenly makes perfect, logical sense. These aren't just random letters and numbers. They are highly precise blueprints. So now that you know the code, what complex carbon structures are hiding in plain sight all around you, just waiting to be decoded? Keep observing, keep questioning, and thanks so much for joining me on this explainer.